today, as you all probably already know, we're going to go over a time series deep dive. So I did have a class earlier on some basics of time series. So ARIMA, moving average models, all of that. So I'm not covering that today because I covered it, but I am going to do some review of some relevant material that will carry over to this week, because I know just in general, there might be some new faces. So if you were at the last one, bear with me. I'm going to go over some of the assumptions again with you guys as a review. It's been a while. So today we're going to be focusing and moving from like the classical time series models and moving more towards models that look at trends and seasonality too. So I'm going to be focusing on profit as well as the time series concepts in general when we're looking at time series that cover seasonality and trends. So today I did pull this particular data set from Kaggle, I believe. So it is a Rossmann store sales. I thought that that would be a great example because in retail, it's generally there's seasonal trends as well as holiday trends, holiday effects as well. So I'm using that particular data set here today. What we're trying to measure and understand. Please mute yourself if you are not speaking. Thank you. What we're trying to measure and learn about today are trends, patterns, and seasonality over time. And the goal is to understand with this time series model, past and current trends. And also I'm going to touch but not get too far into forecasting into the future. All right, so I'll start with an overview of time series analysis. So bear with me if you've seen this before, because this is from the previous class. So I'm doing a little bit of a review from the last one. So I really liked this particular definition and pulled it from some literature. But according to Practical Time Series Analysis, the book, or the time series analysis is an endeavor of extracting meaningful summary and statistical information from points arranged in chronological order. So you guys might be very familiar with regression. Why can't we use regression in order to look at data over time or forecast data over time or understand trends? As you may know, regression, linear regression assumes the independence of observations. So in the case of time series, probably today is pretty similar to yesterday, which was similar to the day before. Whereas if you might go out a year, they might not be as similar to one another. But we can't use linear regression because it does assume that all of our data points are independent of one another. So that's why we cannot use linear regression. So a couple of time series use cases. The obvious one is forecasting into the future. A couple of examples are sales and transactions, orders, things of that sort. Another interesting one would be understanding historical credit card applications, trends, seasonality, and events such as holidays. Another one that's really interesting that I've dug into quite a bit is detecting anomalies as well with the time series. So for example, predicting machinery malfunctions or predictive maintenance with IoT devices. A couple of other use cases are forecasting sales or product supply, detecting trends and outliers in stock sales. So those are just a couple of examples of time series use cases. Now I'm going to jump into the characteristics of time series. Specifically, I'm going to be talking about stationarity as well as looking at some ways to understand if your data is stationary or not. I have gone over this in my previous class, so this is a little bit of a review, but I wanted to make sure everybody knew and remembered about this. So not going to dig into as much detail, but I wanted to do a quick review. So the concept of stationarity is really important for time series. The assumption for many time series models, not the one we're covering today, and I'll get to that more later, is that time series models have statistical properties that stay constant or static over time. A way that I saw when I was preparing for this class, a good way to think about it, I think, is say this time series was broken into equally sized chunks. We would expect those chunks to have the same probability distribution and the same statistical properties. So if that is not the case, then your data is probably not stationary. In general, when a data is stationary, it exhibits no trends or seasonality, and it shows a constant mean and variance over time. So shown down here are two examples of a data set that's not stationary and a data set that's stationary. So shown on the right is the stationary time series. You can see it goes up and down in somewhat random intervals. And if you did cut this into chunks, you would see that it has very similar statistical properties. Whereas most time series tend to look more like the left. So you can see there, there is definite seasonality to it, i.e. it goes up and down at regular intervals. And you can also see not only does it have seasonality, but we're also seeing that the spikes are becoming larger over time, which is also a sign that your data is not stationary, because that means it's not showing a constant mean and variance. So this and this also shows a trend. So it shows all three things that you don't want in a time series. So those are two examples of not stationary and stationary data sets. And I'll get into why you care in a minute. So stationary requirement really tells you what model to use. If you can get your data to be stationary, you probably want to use a more traditional statistical time series model. In this particular case, the ones that we covered in the last class, so it's on my website if you want to learn a little bit more about it. But traditional statistical time series are, example, you've probably heard of an ARIMA model, moving average, autoregressive models. So those are simpler models, and we would think of them as like a traditional time series. One thing that I have probably said throughout my classes is the simplest solution that works is always better. So in general, you don't need to go to deep learning if something similar or something simpler works well. You always want to use the simplest model you can that is effective. So you always want to see if you can use those simpler models first. For example, when I'm doing machine learning, I usually check linear logistic regression as well as ridge regression and lasso regression first. They often don't work, but if they did, in some cases, it's simpler. I want to use it. So Occam's razor, simplest is best. So if you can get your data to be stationary, it's good to try these models. If your data you cannot get your data to be stationary, don't try these models. They require stationary data. One way that you can get data that isn't stationary to be stationary in some cases is first and second differencing. So what is that? First differencing is taking the current time period minus the previous time period. Then the second differencing is using the results from this first differencing procedure and doing a second differencing procedure. So subtracting the previous time period from the current time period. So those sometimes when there's trends and seasonality, sometimes when you do first, second, or even third differencing, it will take that seasonality and trend out and leave you with a stationary data set that you can then use, say, ARIMA models on. I go into, in my other class, when to use like autoregressive versus ARIMA, all of that. So feel free to check it out. So that would be your first line of defense. Are there any questions so far? I am happy to stop here and field any questions you have.
Yeah. Sorry.
Go ahead.
Yeah, thanks. Hey, Helsi. So
Mhm.
basically, thanks for your presentation. I have one doubt. So basically, what you're trying to tell is, we are trying to take out seasonality trend from non-stationary, which means we are trying to predict the random component of it.
Correct. Yes.
So the machine learning or AM ARIMA, it is uh, uh, helping us to uh, predict the random occurrence in future. Correct? That's the
Correct.
understanding.
Yes. Correct.
Okay.
Mhm.
After predicting that, is that we are trying to put back the seasonality and trend?
So you would basically do the opposite of the first and second differencing. So you can basically undifference it, if that makes sense. So you basically take the differencing and you put it back into the data, and
Oh,
that's how you would get it back into the original form. And my other class goes into this in quite a bit of detail. So that's there if you want it for
okay.
sure, because
My
we go
second.
into these models quite a bit.
Okay.
Mhm.
So my quick second question is, these are really very good in terms of sales and marketing data. But for example, the trends in bear and bull market, right? It goes like as is. So what kind of model you can use for stock marketing?
So it really depends on what your data looks like. I can't say that you would definitely want to use one over the other. When you're looking at stocks, I generally Bayesian models work a little bit better for those because it has a random component. It basically runs the model thousands of times and has it basically takes into account the same data can produce something different. So I don't cover those in any of my classes. I haven't used them a ton, so I don't feel
No.
comfortable
I'm just
actually
trying to
teaching them. But yeah.
I'm not particularly thinking on the model. I'm just trying to
Hmm.
understand the data or the how do you call the data, because there's no state. I could not find any pattern to it. But how do you call it? Like this, you won't have any occurrence or seasonality, but it
Hmm.
just goes like anything. So how do you call it? Or
What do you mean
I'm just
call it?
I mean, what kind of uh, the data looks more of random, or it is like a people's emotion of that day. So to apply any model, I have to first understand about the trend or thing. So how do
Hmm.
we approach it is what I'm trying to say.
Yeah, so those are the next slides on how to know when to use what model.
Okay.
So I'll cover that in a minute.
Yeah.
Hmm.
Thank you so much. Yeah.
Yeah. Any other questions? I think there was one other one.
My question was essentially answered. Thank you.
Awesome. Great. Any other questions before we move on? Right. So I did cover this the last time, but I wanted to cover it because the stationary concept will tell you whether you want to use a model that handles seasonality and trend or the traditional time series models. So I had somebody, I was taking a Microsoft training this week, and I never heard it said out loud, but I always have done this. So one of the things that you always want to do in machine learning in general, not just with time series, is try different ways of measuring something. And I'm trying to think of the word, and it's not coming to my mind, but you don't ever want to rely on one measure of something. And this is a great example of that. I'm first going to show how to test stationarity with an actual statistical test, and then I'm going to show how to test it with like an actual graphing method. Um, and I'm going to go into the code right after this. So testing for stationarity. One way to do that is the Dickey-Fuller test, which uses an autoregressive model and it tests for stationarity. And this comes back to the across multiple lag values. So what a lag means is, say we're doing a first differencing. So sorry, that's actually, I'm going to go in here. Okay, so a lag value in this case is, say we go back and this is our first data point. This second data point is like the first lag. So it's basically one data point before. So it looks at different lags or different parts of your time series and looks for stationarity. And in this particular case, the null hypothesis is the data is not stationary. So basically, if the p-value is significant or below 0.05, then you can reject the null hypothesis and assume your data is stationary. So you're looking for statistical significance. So shown here is an example, a code snippet that is showing stationary data. So that the p-value is below 0.05, it's highly significant. So this data is stationary in this particular case. So I'm going to jump in real quick to the notebook. So coming up, you'll see just in general, at the beginning of this notebook, I'm reading in some packages. Profit, by the way, is somewhat difficult to install, especially just in general on Windows machines. It's easier to do it with Conda. They seem to have fixed it on Macs. It used to be completely impossible to install. So it seems to work now. I don't know why or what changed. But there is instructions on the Profit website if you have trouble installing, which really help. Just FYI. And this is reading in MAR data. I wanted to look at the time period. So one of the first things you do with time series is how long is my data? In this particular case, we have from 2013, so the 1st of January to 2015, the 31st of July. So not quite 2 years, which is not ideal for a time series. When you're looking at seasonality, it's better to have at least 2 years. And then this just shows the sales data here. In this particular case, we're doing univariate time series. So we're not using any like regressors or things like to help predict it. We're just looking at the sales over time. So the most simple type of time series. I wanted to see what the mean sales was. So in this case, it's a little over 6 million. That helps us know at the end if our mean squared error, mean absolute error are giving us a good or bad model. And coming here, I often, before you do a time series, so yes, I just saw it's daily data. So does that mean a lag equals 1 day? Correct. Yes, that is correct. So here, make sure before you run any time series that your date is in date format, because you can see that's the first thing I checked. The date was an object, not a date time or a object here. So I then converted it to a date. So you got to make sure your data is in the right format or the model won't know what to do with it. So now looking, you can see that the date has been converted. And here I'm splitting my data into training and validation data sets. I'm going to talk about that a little bit more later on in my slides. So we'll come back to this. So went through, I wanted to see just in general what my distribution looked like, understand the data. You'd usually do a lot more exploratory analysis, but this is a class, so I didn't want to get into that too much. And then I visualized it. So you can see this data. There is a massive dip here when we were looking at the data set. And you can just see that there's spikes and a general oscillating pattern. We see jumps, but we don't see a ton of huge outliers in this data set, which does help. And it's complete in that there aren't really a lot of gaps in the data set, which is also really helpful. Usually in real life, you see gaps in data where it wasn't collected for certain days, and you often see outliers, which can throw off the model. So that's something I'm going to talk about a little later as well. So that shows a little bit about what I did so far. I want to come down to the Dickey-Fuller test that I just talked about. So in this particular case, it is showing that the data is stationary. So this is why I always thought of the word triangulation. So it's the statistical test is telling me that it's stationary, but I don't believe that. So when I look at my data, this does not look stationary. So I immediately look at that and say, not so sure I believe that. And there's a good reason I didn't believe that. And I'm going to show you the next way of looking at it. So I'm going to come back to my slides. So this shows the statistical test. Now, go ahead.
I'm sorry, I have to interrupt. I have a question here. Looking at the graph, when you say that data is not stationary. What makes you say that?
There's a big trend. So specifically, definitely this part. So stationary data has the same statistical properties, so same mean and variance. It doesn't show a trend, and it doesn't generally show seasonality. So immediately I'm seeing, if I broke this into chunks, this part would show different statistical properties than this part or this part. So I don't believe what the statistical test is telling me, because there's no way it's stationary, and it's actually not. And I can show you the next test and show you how we know that.
Yeah, but this is definitely not trend, because trend is for a long period of time, you know, but this could be seasonality, but definitely data is not stationary.
Correct. Yes. So those are the options, but in this case, the constant mean and variance is very clearly not here. So that's really where I don't believe the statistical test when it's telling me that, because constant mean and variance is not here. So that's why I immediately said, don't believe it. Can't always believe a statistical test. That's why we do triangulation, to make sure we're right. So, and this is how I know it isn't stationary. So gonna come back real quick. So I'm going to talk a little bit about autocorrelation before we get into the next plot, because it comes into play here. So autocorrelation is correlation between two data points in different positions in the time series. So coming back to the lags, autocorrelation is measured in lags, or the number of intervals between 2 points in a data series. For example, the lag between the current point and 2 points prior is 2. So coming back to, and if it's the point after the current point, the lag is 1. So that's how we know it's basically, in this, just like the question said, this is daily data. So one lag is 1 day. So that was a good question. And examining autocorrelation plots can help uncover whether something is stationary, and whether it shows seasonality and trends in general. So that's another way to triangulate and tell whether your data is stationary. So here is an autocorrelation, or ACF, you might hear, plot to see if your data is stationary. So we know that the bars outside the red lines have autocorrelation that is significant. If you do see a couple of bars outside of significance, that's not a big deal if they're one of the first bars. So in general, stationary data usually has 1 or 2 high bars. And then once you go farther out, by that I mean more lags, they are no longer significant. So basically, when you're 3 data points away from your current data point, they're not highly correlated anymore. That's what this tells. So the third lag is not statistically significant. We would expect this to go down quickly in stationary data, which is what's shown here in this particular plot. This is stationary. Now I want to show a couple of examples of when data is not stationary. In this case, this is a completely random data set that somebody generated, and they did an autocorrelation plot on it. Time series doesn't work for something that's totally random. So that's what's shown here. You can see that there's no spikes at the beginning or large bars, meaning that none of the points are correlated with any of the other points, which shows that it's not time series data. it might be something that you can use a regression for instead of time series. Shown here is a trend. So in general, you're going to see in an autocorrelation plot, the bars go down only slightly, very slowly over time. You can see that here, and that shows that there's a trend in your data. Seasonality looks a little bit different. So in general, the bars oscillate. So move up and down, and you see kind of a seasonal oscillation with it. So if you see this, you know that your data, it has seasonality. So in these cases, unless they're differenced, and sometimes differencing doesn't work, or you want to actually have a model that takes into account seasonality. In this case, that you would want to choose your model based on this. So coming back real quick to the code, we're seeing here, this is not a correlation plot of the particular data set that we're working with. So I think it was Neelam, right? You said that there's no trend in this data set. You can see here that you were right. There is no trend in this data set. We're not seeing the slow down slope. However, we are seeing seasonality.
Fluctuations.
Yep. So we're seeing the fluctuations or the oscillating pattern. So this tells us that our sales data, which it's sales data, so obviously it probably has seasonal trends, has seasonality. Usually with sales data, you'd see trends too. With this particular data set, you don't. So we know from looking at this oscillation that our data is not stationary. We also see the oscillation at the bottom too, as well. So this is telling us that there's seasonality in our data. So theoretically, I could go try first, second, and third differencing on this data and see if I could get it to be stationary. In this case, though, I don't really want to. The reason I say that is sometimes you want to understand seasonality. Sometimes showing that to stakeholders and understanding what your seasonality looks like and understanding those patterns is good. And sometimes when data is highly seasonal, it also helps you predict well. In this particular case, I want to use a seasonal model, particularly because of that. And also when you use a more sophisticated model, you can include things like the holiday effect, which is really going to show up in sales data. So $20, this was Christmas. You can't see because the particular like transformation that it changed it to numbers, but in general, at least in grocery, when I worked in grocery, you saw a large dip in summer. People apparently don't get as many groceries in summer. I don't know why. But then you would see a large increase around Thanksgiving and Christmas. So models that have seasonality in them can help. You can look at those things like holiday effect. You can look at outliers and control for them. That's what we want to do today. But this confirms, unless we did some manipulation to the data, and a traditional model wouldn't work in this case. And even if it did, I really kind of want to go forward with something else, because knowing my data and knowing that it's sales retail data, seasonality is very important in that particular field. So coming back to my slides. So just in general, what if you cannot achieve stationary? First, second differencing, you still have trends and seasonality. That means you usually need to move on to a different type of model. And in general, you might want to use another model if we're looking at things that generally have a seasonal trend anyway. So one option is to use the SARIMA or a seasonal ARIMA model. That's not what we're going to cover today. I'm going to cover another model called, it's created by Facebook, Facebook Profit, because it has some really interesting aspects of it that are, I don't think I've ever used it for forecasting. I always use it to help stakeholders understand their data. So I'll be talking about that and going through that as well. Are there any questions? I'm going to stop and pause for a moment.
I'm just curious, you said the profit model you used only for analysis and not for forecasting, why it is, and I'm just trying to understand what is about it.
So I just didn't have a use case in the job where I've used this where they wanted to forecast anything. It wasn't just because you can't. Where I work now, they use it for forecasting. Now they try a bunch of different types of models, and this one came out as one of the top ones. And I've just used it in general. Time series is good. So say you're trying to sell something. I was like in consulting and I work for a rewards and incentives company. If you're trying to sell something or sell a project, time series is really good because, especially this package, because when your stakeholders can see something in your data and in your visuals that they recognize, it makes them more comfortable. And often Profit can give insights that they expect to get, things that they've seen before. And then it'll also give them some additional insights that might be really valuable too. So I like to use it in that case as well to understand data, and it can be used for forecasting. So it can be used for both. Nothing's wrong with forecasting with it.
Yeah.
Yep. In general, I'd try multiple models. That would be my one suggestion. Never do one model and call it good. So in this particular case, I'm not going to show this in the code because there wasn't like case for it with this particular data. It was cleaner than you'll ever get in real life, which is why Kaggle isn't always the greatest place to learn. But in general, you might have missing values. So Profit actually handles missing values really well, and you don't often even have to impute. Facebook created Profit as the dummy time series for dummies. Apparently at Facebook, their data scientists who didn't have time series knowledge or specialty weren't using time series models right. So they created something that worked well for across many use cases. So it's like, it's harder to screw up, basically, is what they did. So it's a great one to learn with for sure. But it actually handles missing data pretty well, so you could impute or not. But a couple of things for pre-processing and getting rid of missing values. There's a couple of ways to do that. Forward fill is one, so carrying forward the last known value prior to the missing value. This should not be used for forecasting and prediction. Why? Because it creates something, it's similar to leakage. I'm going to cover that in just a second. It basically, you're including, in a forecasting, we're including parts that won't be available in production. Like, so we're basically cheating. I'm going to cover that more in a second. Backward fill, if you're forecasting, you might want to use this one. Fill in data backwards with the nearest known data point. So basically backward fill. Another option is moving average, so a rolling median or average with multiple data points before or after the missing data point, or both, actually. And another option is exponentially weighted moving averages, which actually gives higher weight to those closer by or more recent data points. So that's an option as well.
Kelsey, it feels like forward would or backward would be leakage and forward would be, am I just getting reversed on the terminology here?
Forward fill would have a leakage because you're taking from, so say
we're doing January.
Mm-hmm.
Is forward pulling from December or pulling from February?
Pulling from December. So say January 1st is missing and December 31st isn't. It pulls from, pull December 31st and put it into January 1st. So it's basically pulling from the back.
Because we wouldn't have that in the future.
So it's basically using data that shouldn't be like in your training data set. Right. Yeah, it's basically pulling from the past, and it's telling you future stuff that the model shouldn't know, basically. And they called it something a little bit different. Lookaheads is what it's called, and it's similar to leakage. But when a model replies on data not available or known during the time period being modeled. So
Yeah.
Mhm.
Yeah, I recognize this problem very well.
Yeah, so it's something, it's a pitfall to be aware of, which is why I'm mentioning it. But so if you want to avoid that, so it's not a problem if you're not forecasting. It's not an issue. You can do whatever works best for your particular data problem. But if you are forecasting, you're going to want to use backward fill or a moving average using the data after the data point only. And which one works best will depend on your data set and the domain as well. So maybe they don't make sense. And a great example, January 1st. So say most grocery stores are closed on Christmas. So you can't really pull Christmas Eve over into Christmas, because Christmas Eve's probably pretty busy because people are doing last minute. And if you pull it into Christmas, the day that nobody worked it's getting pulled in. So it's not missing at random. So there's just generally, you'll have to experiment, try to understand why your data is missing and figure out the best way to do it. And other pre-processing methods that you can do, so data aggregation. So a great example, if you say you're using IoT devices or something like that, and you have multiple data sets, they might be captured at different times. So say one goes every 2 hours, one goes every 3 hours, and you need to match it up, for example. Or if you want to get rid of noise that's caused, say daily data is really noisy, it's not predicting well, you could actually roll that up into weekly data, for example. So you can re-aggregate your data, either to align data sets, make them on the same level, or decrease that noise to make predictions more accurate. You can also sometimes smooth your data, which removes random variation in general, and it pulls out the traits and the structure of the time series data. And that can improve predictions, especially when the randomness and the variation isn't helpful for predicting the actual trend. So where oscillations matter, this isn't going to be a good idea, but it can work, and it's something that you can test. So coming back to the look ahead, you also need to be careful about the look aheads when you smooth your data too. You can only use data after the data point to smooth if you're going to do that. So you want to avoid a look ahead, or your model is going to have inflated accuracy more than it will have in prediction time in its deployment. So just something to be aware of. All right. So I'm going to go a little bit into the profit models now. So profit models, I already told you a little bit about why they were made. But one of the reasons you'd want to use this over an ARIMA model is it allows you to pull out seasonality and trends. It also looks at change points, which I'll cover in a second. And it also allows you to look at holidays, which is super helpful for sales data, which is why I actually chose it for this particular use case. So it allows you to look at daily, weekly, and yearly seasonality. So anywhere back to hourly data and you're looking at daily patterns, it will look at that too. It also looks at general movement or trends over time. It's all called a time series decomposition model because it decomposes the particular time series into separate parts, being the trend, the seasonality, and then the random variation, and also any regressors that you would put in. It will break them out into their component parts. So that's why it's called a time series decomposition model. So it also looks at random error or noise that cannot be directly modeled. This is very important. I'm going to come back to this. Your error tells you a lot about how well your time series is working. So we'll come back to that. It allows you also to put extra regressors in there. A great example of when I've done that in the past is I'm looking at data where, say, we've had promotions, and I'm looking at data, and we have times where there's no promotion, and we have time where there's different promotions. I would put the promotions in there as a regressor, for example. All right. So digging a little bit, actually, I'm going to stop here. Are there any questions? I'm going to dig into the details of each of these independently, but just in general, are there any questions?
Hi, so it sounds like a trend and seasonality. The difference is the time frame. If
not really.
No. Okay.
Yeah, so I'll show a little bit more of that. It's not really seasonality. So say I'm going to give an example. So I already gave one. So in retail, in grocery in particular, there's a summer slump every year, no matter what. There's always a holiday spike. That's seasonality. So if we looked at data over 3 years, we would see that every year. And it would differ a little bit, but that's called seasonality. Also, in general, Sunday, Saturday, and Mondays for grocery, there are more shoppers every week. And that's called weekly seasonality. Does that help?
Yes.
And trend is like it's changing over time across the whole time series. Awesome question. Thank you. All right. Any other questions just in general about that? And I'll show a visual of that in a minute.
Kelsey, hi. I have a question.
Yep.
What are the other last 2 points, change points and extra regressor?
So change points I'm going to cover in a slide coming up. That one's a lot easier to see with a visual. Extra regressors are just kind of like linear regression. It's adding a regressor. That's what I was talking about when I said I added promotions as a regressor. It's basically controlling for the promotion, whether there was a promotion or what kind of promotion. So it was telling the model that during that promotion, it was different. So it would control for it and pull out the impact. Well, impact, I wouldn't use that word, always use that word lightly, but the effect of that promotion. So
okay.
And then there's a couple more examples, I think, later on.
Okay. Is change point also something like COVID situation? Something
Let me
like
cover that in the next, I have a slide on that. So yeah, hold that question. And if I don't answer it, then we can circle back. Yeah.
Thank you.
I have a quick question, maybe the previous. So how do you tell the system, is it a 0 point or is it a missing value?
So for missing values, you would fill in the missing value.
I'm just trying to say when there is no sale, you'll have 0, which means no sales at all, which it can be 0. And
you wouldn't have 0. So you would have 0 if there were no sales. You would have a missing value.
So how do I tell the system, is it a missing data or is it 0?
The system would know. Like if it's an NA or a null, it wouldn't assume 0. It's just the code
so
would
which means
know.
My data point should have NA. Okay.
Yeah. So if it's null, it knows. Yep. For sure. Yep. Only if you have 0 in there will it assume 0. Any other questions? All right. Might go a little late today. Hopefully that's okay with you guys. So talking a little bit about trend. So trend over time, there are, you've heard of hyperparameters probably in machine learning. They're kind of similar in time series, but I would say there are more choices. You can change the trend that profit assumes. The most common one is linear growth, which you can think of that as a piecewise linear function. So think y equals mx plus b. So similar to a linear regression, but we would have different slopes between the different change points. I would say 90% of the time you're probably going to use this. Logistic growth is good when you have a bottom and a top. So a great example of that, sales can't go below 0. Sometimes your model will predict negative sales. That's not something that's actually possible. So you might, if you're getting predictions of negative sales, logistic growth allows you to set 0 as like the lowest you can get. And if you know, because of your data's domain, that there's a max value, you can set that as well. And you can also set a flat trend if there's no growth over time at all. The model would probably pick that up anyway, so I can't see a place where I would use that in general, but it's an option. And you can set the growth parameter in the profit model function itself. So I'll show how that's done. This one's really important. Additive versus multiplicative seasonality. So you can see here, there was a question of what's seasonality. In general, both of these show very heavy seasonality, both of these figures, because we're seeing an oscillating pattern at the same time, or the same intervals, I would call it. But we're seeing two different types of seasonality. Additive up here, we're seeing a trend. This has nothing to do with trend. This is only looking at the actual changes or oscillations themselves. We see here that over time, those oscillations are staying pretty consistent over time. They're not getting larger or smaller over time. When we have multiplicative seasonality, that the oscillations are actually getting bigger over time as time passes. So what this allows you to do, and I guess this is a great way to say seasonality is added to the trend versus seasonality grows with the trend. So we want to know if our seasonality is increasing, decreasing, or staying the same. And by looking at your data, you'll be able to see just in general, are the oscillations changing, and you can set it to be additive or multiplicative in the particular profit function as well. So telling it what kind of seasonality to expect. Now we get to change points. So this is really interesting. This I really like to show stakeholders because it's sometimes really helpful. So a change point, Profit does automatic change point detection. So change points are abrupt changes in trajectory or trend of the time series. So I was working with an airline and looking at rewards for that airline. I think the question was about COVID. So when the airlines basically shut down, the trend went to, it was like, boop, that was a change point. Now it's a little bit different. The underlying data just completely changed. I would say that it's a change point, but it's also something else entirely as well. But it's basically the trend shifted, or there was a pivot. So if you're coming up, you see kind of a curve, or the trend or slope changed. So you can think of it as that. So it goes through and plots a bunch of potential change points. And it looks for change points in your data itself. And you can output really interesting visuals of when those change points occurred. So when I was working with a retailer, I was actually tasked with looking at the holiday effect. They wanted to understand how things change during holidays, but the analysis actually then became about severe weather. Because when severe weather came about, we were seeing all these spikes we weren't suspecting would happen, and we're like, oh, I wonder what that spike is. I would Google it and there would be a severe weather event. It's like, okay, so everything that wasn't explained by holiday was explained by severe weather event. So every time I saw that fluctuation or change point in sales, it was usually a severe weather event that we found that caused it. So that's what change points are. It's also, the model tests, I think by default, 25 different change point areas. You want to be careful of that parameter, because if it's testing too many change points and your data isn't long enough, it may overfit. So does that answer the question about what a change point is? I take that as a yes. Hope so. All right. So you may have heard of this just generally from machine learning. This actually shouldn't have change points on it. There is another thing called regularization, or actually it can be change points or not related to change points. So regularization basically helps prevent overfitting. So it, in some cases, can make the trend more or less flexible over time. So in this particular case, you can change that flexibility. So say you had 25 change points, your model was overfitting, you could change that parameter increase the regularization, and it would allow you to have a more flexible trend and decrease overfitting. So that's just a hyperparameter. I cover regularization a lot more detail in, I believe, class 4 of my series when I talk about ridge and lasso regression. So I'm not going to get too deep into that. The other really interesting thing that you can do with Profit is holidays and regressors. We talked about regressors a little bit already, but you can actually specify holidays or events and windows surrounding them to measure a recurring holiday effect. This would be really important around Christmas, New Year's, around Labor Day, all of those, especially when we're talking about sales. So you can specify different holidays. And the really cool thing about Profit, you can actually use an option of built-in country holidays. So you could put that, since this case, it's the US data, you can put in the US, but I've used this before where I was looking at global data. So for Russia, I put in Russia. For I believe China was in there, I put in China, so on and so forth. And it actually takes the holidays from that country and puts it in your model, which is really neat, I think.
Are holidays important on like monthly data, or does that kind of wash out a little bit more?
Yeah, you wouldn't be able to put it in there because it's, since a holiday is a day. Now, potentially, if you're looking at something like sales, monthly data, like the holiday effect of New Year's and Christmas is so long that you could probably do it there.
But that would probably show up as seasonality though, so it's probably
if
coming
you
out
have
in the
more
wash.
than 1 year.
Yeah.
Yes.
Okay,
Mhm.
thank you.
And then the other thing is custom seasonality. You can do that too. If you know, like I believe when I worked in grocery, we put the summer slump in there. We actually put seasonality, like we said the summer was, it was either summer or not summer, and it helped our model a little bit. So because we knew that that was just seasonality that we expected in that particular domain. So I'm not going to go over these because we're running out of time, but these, for your reference, are a couple of parameters that you can put into your model to change it and make adjustments. So here I showed a couple of the images from Profit's website. So they, I think, looked at points for like the NFL, and I am not a football person, by the way, so I apologize if I butcher this. But you can go in, you can see here in general, and I'm gonna zoom in. This is generally what Profit looks like, and it doesn't, here we go. So the first part that it would show is the trend over time. So you can see that here. We also can see holidays. And then we see a weekly trend, so Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And then we see a yearly seasonality too. And this is an example. This is what adding a regressor would look like. So NFL Sundays in this particular case. And then you can also do on or off season. So on season, off season. So these are basically visuals of what I was talking about for those different options. But now I'm going to go back into our code, and then I'll stop for questions at the end. And so here it shows our profit model. So here you can see, I really like it because it's extremely simple too. So we have our data. One of the things you have to do is they have to be named DS and Y, or it will not run. So your date has to be DS. It has to have the variable name DS, and your value that you're modeling has to be called Y, or it won't run. It'll yell at you and give you an error. So you have to set the model object, which in general, we've talked about that in my class quite a bit. And then you have to fit the model object with just like you would normally in machine learning. And then here, I am doing forecasting. So I want to forecast the next 92 days of sales. So that's just a number I picked. It's not, I didn't choose that for any particular reason. You would have a reason in like a real case where you knew the domain, you would have a reason for the number you would put in here. And then you can you use to fit and to get those predictions out, or to get the trend seasonality, even if you're not predicting anything, to get all that information out, you have to use the predict function. If you're not predicting anything, this would be 0. If you're just understanding the trends and the seasonality, you would put that as 0. So you can do this without predicting anything. I mentioned that. It allows you, also there's an R package for this, by the way, now that I'm thinking about it. So this shows here a plot of this particular data set. So we can see those oscillations. It also shows the confidence intervals around them. And you see here that there are change points. Okay, hold on. So I want to zoom in. It's not super apparent on this unless you go really far in. So here we can see that there was a change in trend at these different points. You can see where the trend was relatively flat here. There was a change in trend here. This one's the most apparent. It was going down and then it was flat. So that's what's shown. These are significant change points. So you can see here it's going up, then it's going down. So that's what a change point is. This isn't a great visual, just in general, because it's so zoomed in, but that is what they are in practice. And you'll see here our plot components. So we can see in general, it pulled out the trend that looks like this. So there was an increase, a decrease. So this would be the change that is not accounted for by seasonality or random error. It has the weekly trend. So in this case, they may have been closed on Sundays. I don't know. But on Monday was their most busy day in general. But there wasn't a lot of decrease. Saturday isn't busy, which is very strange. I wouldn't have expected this from sales data, but it's a Kaggle data set. So you can see here, lo and behold, the increase that we saw was a holiday effect. I said $20, it's because I actually didn't look. $20, it's around Christmas and Thanksgiving, and it was. So that was the pre-Christmas spike that we saw on our data set. And it was relatively flat throughout the year, and a decrease before the holidays. So that's what it pulled out in this particular case. So this was the default model. I didn't do anything to it. I didn't change anything. It was like me just using the out of the box method. Then I tried a couple of things. Oh, before I move on to that, here are also the change points. So the model pulled out our potential change points shown here. And we can see the magnitude or the rate of change at these change points. It's relatively small. You saw that on the actual graph, and when they changed, it didn't change much. So we can see in general, like there was a 2% change here and a 6% change here. So that's what the change points outlook looks like. And then I added the dates to the bottom. I have That annoys me that they don't put dates on the change points. It's very odd. So here are the change points by date. So for example, in 2013, right around Thanksgiving, that was like right before Thanksgiving was a decrease in 6%. So you can see that up here. So, all right. And this is what the output looks like. So it gives you a trend, and then it gives you a confidence interval around that trend. Or so this is the confidence interval around the trend. It gives a prediction and a confidence interval around that prediction. It gives our weekly seasonality. These will be repeated. You're going to see every Monday will have the same value. So you're going to see, like, if it's head, so I can't see it, but these values will be repeated for every Monday. It'll have the same value. Same thing with yearly. So January 1st is going to have the same number in this data set as well. Then it has additive or multiplicative terms, depending on whether they use an additive or multiplicative model. In this case, the default is additive, and then it gives a prediction, which is our y-hat. And I just showed down here a smaller version of that, pulling out the predictions. And this shows our predictions versus our actuals. So we're seeing that in general, it's predicting pretty much a static trend, and it's not catching the larger spikes. So this doesn't look like a very good model, and we'll see that more towards the bottom. So for the rest of them, I changed or tweaked a couple things. So in this one, I added the country holidays, so US holidays. You can see here, this is what our holiday effect looks like. So we can see that, again, on the holiday, or on the holiday itself, it tends to go to, the store's usually closed. So you're usually going to see a big drop. And then you're going to see a spike before it. That's generally what you see in retail, our weekly and yearly seasonality again. And our change points. I changed it from additive to multiplicative, our models, and kept the holidays in as well for this one. So in this case, looking at our data, the oscillations looked like they weren't static over time. So tried the multiplicative function. And then I also changed the regularization. So I basically made the model have a more flexible trend to reduce overfitting. So in this case, using the change point prior scale, basically to add regularization. And finally, our model metrics down below. There was, I would call, close to a tie. So the default was worst by far. So this was the default profit model. None of these are good. Let's preface with that. This was a terrible model. The average sales was 6 million, and we're seeing an MAE that's like 1.3 million. This model's terrible. You would want to use something different or make adjustments. This was just kind of a toy example. So our profit model with holidays got a little bit better with just holidays. And then it got a little bit better. Both of these are essentially equivalent. Some of them are higher, some of them are lower. So I went with model 3 as our best model, I would say, best model. So the MSE, mean squared error, was lowest on this one, meaning generally it's getting the spikes and the dips better. It tends to be higher when it's missing by a lot, the model. The MAE is not the lowest. It is lowest in the model 4, but often for time series MAPE, or mean average percentage error, is the best one to use anyway. And it's lowest, or it's lower for this model. So you can see, again, triangulation, trying a different thing, trying different things. It's pretty much a crapshoot between these two, but they're the better models here as well. So in order to do that, I did forget to talk about validation. So in order to validate a time series model, you would normally do like k-fold cross-validation or a holdout data set randomly chosen. You can't do that with time series because the data is correlated over time and it wouldn't make any sense. So usually you chop off part of your data set. So you hold out or take out a certain amount of your data and use that to test and validate whether your model is good or not. In this case, it's terrible. This model's not good. So that the model performance can be judged on unseen data. So that's what this is showing here and what the mean squared error and MAE and MAPE are showing just in general. And the reason I calculated, or one of the reasons I calculated the average, is the average daily sales are 6 million. The error on average is 1.2 million, meaning that the model is really bad. So in general, we're missing by 20% or more most of the time. So your MAE, there's no good MAE. There's no good MSE because all your models are going to be on different scales. There is no, I always get that question inevitably. What's a good MAE? What's a good MSE? There is none because you could be looking at something where your data ranged from 0 to 1. And you can be looking at something that has a high magnitude like this. But I do know that if our average daily sales are 6 million and we're missing by 1.3 million, that isn't good. So that tells me that my model's not great. Mean average percentage error looks a little bit different, a little bit better than that. But in general, there is no good or bad. You're usually comparing multiple models against one another. And then when something's really bad, it's usually pretty apparent. Like in this case, we're missing by a very large percentage in this case of our average sales. So that's something to keep in mind. So real quick, I'm going to jump back. So the way that I split this up, it's very simple. It's a simple indexing procedure. So in this case, I took like our max date and our min date are shown here, and I basically chopped off a couple of months to do this validation with, which is shown here. So that's what I did there in order to do the test. So our test had 92 days in it. So, and that's where our predictions came from. So 92 days. So we were making predictions on known data and comparing it. So that's what we found with that particular data set. So to sum up, profit can be used not just for forecasting, but for a lot of different things. So as you can imagine, showing somebody their change points might be really helpful. If we need to plan staffing, understanding when there are large fluctuations is going to be really important. We also want to understand change points because say we want to plan a promotion. Maybe we want to plan a promotion when there's more people in the store, things like that. So outliers and abrupt changes are interesting to stakeholders. They also probably know about already their seasonality over time. So often showing them that it helps confirm that you know what you're talking about, that your models are working. So it's actually a validation exercise, often with people who know their data well. So I already went over some examples, but hopefully this was helpful. I have a couple more minutes. Are there any other questions? I can stay for like 5 more minutes.
I had a question. In your data fit that you said was not that great, it looks like there's some peaks that weren't predicted on that chart.
Yes.
Could there be perhaps another regressor added in the formula or some volatility range factor that could be picked up off a time series and added into the formula to give you more volatility?
Yes, I don't think you can with this model. That's one option, but honestly, what I think it really is is that it's seasonality not picked up by the model because we don't have enough data. So we don't even have 2 years. So in general, some of that seasonality is not going to get picked up by the model because there's not enough time to show it. That's what I think is really going on here. If we looked at our residuals, I bet you'd see seasonality in the residuals. I actually didn't look at them. So
makes sense. Yeah, usually 3 years is what you need, right? Okay.
Minimum 2 years, like, because then you can see the yearly seasonality really well. But 3 is much better. Yeah.
Thank you.
Hey, Kelsey, really enjoy your class here. Can you talk about your experience with ARIMA and Profit? Which one do you think is working better for you?
I think it depends on what your data looks like. So I actually taught the ARIMA class and used the Missouri drug overdoses for that. Well, it was also monthly data, which Profit does not work well if it's not daily data. So that's an example, like you can use it, but you probably shouldn't use it. So ARIMA worked a lot better, and it was a better example for that. There's not a whole lot of seasonality in these. There's a large trend that we got out by differencing. But it really depends on your data. Now, if you can get your data to be stationary and seasonality is not really what you're focusing on, or you don't want to understand it, or your data is not highly seasonal, even with a trend like this, I was able to get it to be stationary. Again, Occam's razor. Like if it works well, use the simplest method unless there's a good reason not to. Now with this, there was a pretty good reason not to use ARIMA because holiday effect, seasonality was big. Just in general, this data set looks like ARIMA would be a nightmare because it doesn't fit the data set. But if ARIMA or traditional models work well, I do recommend using them because once you add more complexity to your model, it has more risk of overfitting, of running into problems in deployment. So simpler is generally better unless there's a good reason not to use it, which often there is. So it's really what your data looks like. ARIMA is overused. Any other questions? All right, going. All right, we'll call it a night then. Thank you guys for attending. I really enjoyed it. Hopefully you learned something. And my upcoming class is anomaly detection. So feel free to join that as well. Definitely going to be digging into that quite a bit and looking at different methods of looking at anomalies over time. So hope to have you there. Have a good evening.
Thank you so much. Thank you. Bye.